Welcome students, welcome to the next session of Strength of Materials 1. So in the previous class we have started our third unit, which is bending stresses in the beams. There we have started the definition of pure bending action and started assumptions involved in the pure bending theory. Now we are going into the expression for generating the pure bending theory's equation. The first thing for the analysis or for generating or giving the expression, I am taking a segment. Okay, so I am considering a beam which is having a pure bending or constant bending only. So it will not have any shear force, purely bending action is there. So in such a type of beam I am taking, in that beam I am taking a very smaller element of length delta x, which is in between the sections AB and CD. So those two sections are parallel to each other and being perpendicular or normal to the axis of the beam. Okay, so this segment is like this and it is having two cross-sectional planes like AB and CD, and between those two we are having a length of the element as delta x, and the center line which we have indicated is axis of the beam. Okay, now consider two transverse sections AB and CD which are being normal to the axis of the beam and parallel to each other. Now the layer, due to the bending action, what is happening? Due to this bending action, the element ABCD in initial only, this is like a straight line, only without any stressed condition the segment is there. But due to the application of some bending, what is happening? This segment is distorting its shape to A dash B dash C dash D dash. So the overall ABCD structure is distorting or deforming to A dash B dash C dash and D dash. So the layers of the beam are not of the same length as the initial condition. So before applying the bending action, the length of the layers are not at all having the same length after the application of bending. So initial length of AC is something. After the bending action, the length A dash C dash value is something, and initially the length BD is some value. After the bending action, it is having B dash D dash as the length. You can observe clearly here, this picture itself I am explaining as a statement. Okay, so initially ABCD is there. Due to the application of bending, it has distorted to some new shape, and initial length of any element or any filament is, or any layer, as we have already mentioned, the beam we are assuming as a layer by layer like structure. Okay, so those layers are not having the same length after the bending action. Now the layer AC is shortened to A dash C dash and it is being subjected to compressive stress. So shortening, initially it is having some length as AC, but due to the application of bending action, it has become like this. So initial length of AC has shortened to A dash C dash. So what is happening? When the length or its dimension reduces, when we apply some compressive stress only. So on this AC, there may be some application of compressive stress. Even though I am applying load in the form of perpendicular or bending action. Okay, here I am applying load in this direction. But what is happening? The members or the layers are getting shortened. Even though we are applying load perpendicular to the axis, but the layers are getting shortened. Why this shortening happens? Maybe some application of compressive stresses has generated. Similarly, the layer BD is elongated to B dash D dash. So initially BD was like this, but as it is being the bottom level, you can observe B dash D dash has elongated, as initial length but not same as A dash C dash length is lesser, B dash D dash length is more than the initial one. Okay, so how the length is getting elongated? When we apply tensile force only. Here also the same thing, so that there is an application of tensile stresses on this layer. Okay, now hence the amount of shortening is decreasing from the top towards the bottom, and the amount of elongation is decreasing from the bottom towards the top. So the amount of compression or shortening. So initially in the top layer we are having reduction in the length, later on it is reducing lesser towards when I am coming down. And therefore, there is a layer in between, neither elongation nor shortening. So we have said in the top I am observing some shortening, in the bottom I am observing some elongation. In between those top layer of shortening, in between those bottom layer of elongation, there may be some layer with zero elongation. That layer can be called as neutral layer. Neutral layer without any elongation or without any shortening. So, in between those layers which have got elongated, which have got shortened, in between those two layers, there is a layer with zero change in its dimension or zero change in the length of the layer. That is neutral layer. Now, the filaments or fibers of the material are subjected to neither compression or nor tension. So, in this neutral layer, those members, maybe it was like a single slice. Okay, so one slice it is like this and it is not at all getting elongated, not at all getting shortened, but simply it is taking the shape. Just it is taking the shape without any change in the dimension of the length. Because in the top I have observed shortening, in the bottom we have observed elongation. But in between those two, we have observed a layer without any expansion or contraction, or without any shortening or without any elongation. Okay. The line of intersection of this neutral layer with transverse section. So, I have mentioned this is a neutral layer. Okay. This is neutral layer. Now, the line of intersection of the neutral layer with the transverse section. Transverse section means simply like a knife. Imagine. So, when one knife is cutting this overall beam. So, with this we are cutting. Okay. So, some transverse section I am observing. Now, in this transverse section, this neutral layer is also there, right? So, this neutral layer is also there. Now, the line of intersection of the neutral layer and the transverse section. This line is there, right? So, this horizontal plane and there is a vertical plane. So, in this way, the line of intersection of the neutral layer and the transverse section, there you can observe an line. That line of action, we are naming it as neutral axis. Line of intersection of the neutral layer and the transverse section. Two planes meet, it will give line. All these things you will learn in the engineering drawing also. You should have to imagine more what is happening. Layer by layer they are responding, layer by layer they are contracting. In the bottom we are observing some expansion. In the top there is some shortening. In between some layer there is no change in the dimension. Now, in that layer is being connected or connected with a transverse section. So, the line of intersection of a plane with one plane. Two planes are being connected and it will give a line of intersection. Two lines connect will give point of intersection. Okay. So, that is line to line connection. Here, plane to plane connection. Okay. When plane to plane is meeting, it will give a line of intersection. That line of intersection is neutral axis. Now, the layers above the neutral layer, NN. So, in this picture itself, we have given that axis of the beam. When we observe the side view, the layer portion will be there like a plane or a plank or a paper. Okay, a simple light A4 sheet or a paper is there. So, that paper I am indicating as neutral layer. Above that, there is some compression in the dimension. Below that, there will be some elongations or tensions in the dimensions. And the layers above NN have been shortened. Yes, because it has highest shortening at this level. And at NN level, there is no shortening. And in the below, we are having highest elongation. Okay, so the layers above NN are getting shortened and below are getting elongated. Due to decrease in the length of the layers above NN, these layers will be subjected to compressive stress, as we have already mentioned. So, as the length is shortening there, each layer like this, as I am observing the side view of a pile of slices. Okay, so number of slices were there and I am giving some load like this. So all the slices are giving some arc shape in the side view. When we observe this side view, I can observe like this. Okay. So like this, slices will be there, layer by layer they were placed and piled up. Now on those pile up I am giving the bending action, and in the top portion I can observe some shortening. In the bottom portion we are observing some elongation. As we have observed, shortening is occurring due to the compressive stress action. So above NN, above the neutral layer, there the layers will be subjected to compressive stress. Due to the increase in the length of the layers below NN, the layers will be subjected to tensile stresses. So above the layers will have compressive stresses, below layers will have tensile stresses. We see that the top layer has been shortened maximum, highest decrease in the length. So compared to the remaining layers, see here, compared to the remaining layers, topmost layer has highest shortening. So more change in the length is observed in the top layer. As we proceed towards the neutral layer, NN, okay, the decrease in the length of the layer also decreases. Top, I am having reduction in the length of 5 mm. Maybe after some time 4 mm length decrease, 3 mm length decrease, 2 mm length decrease, 1 mm length decrease. So this was in the top. So it has reduced by a length of 5 mm maybe. Okay. And I am observing the next one. It has reduction in the length. Delta L we will write change in the length. Okay. Reduction or change in the length is 4 mm only. And maybe next time change in the length is 3 mm. In this way, when I am reaching delta L is equal to 0 in case of the neutral layer, each layer is showing some change in the length. Okay. Now, when we are moving towards neutral layer, from the topmost layer, the decrease in the length is decreasing. So, this is the decrease in the length. 5 mm decrease in the length, 4 mm decrease in the length, 3 mm decrease in the length. So, the values also getting decreased. So, decrease in the length is decreasing. This means the compressive stress is high at the top and it is reducing towards the neutral layer. Okay. So, the compressive stress action acting on this layer, even though I am applying the load in this direction, some compressive stress is acting on the layers, and that compressive stress is maximum in the top layer compared to the remaining layers. Now, at the neutral layer, there is no change in the length. Similarly, in case of increasing the length, I am observing the neutral layer, and at the bottom we have got this is the bottom layer, as I have indicated as B dash and D dash. Okay. So this is the bottom layer, and it has got increase in the length as 5 mm maybe. Okay. 5 mm increase in the length. On this above, another layer is there. It has got some lesser increase in the length, which is 4 mm. And above that, it has somewhat lesser increase in the length, which is 3 mm. In this way, when I am coming towards the neutral layer, what is happening? Similarly, increase in the length is maximum at the bottom layer. Increase in the length is maximum at the bottom layer as we proceed from the bottom layer towards the neutral layer. Increase in the length is also decreasing. Okay, so these increased values also decreasing, and hence the theory of pure bending is stating something. So the theory of pure bending states that in a beam which is being subjected to pure bending only, not the action of shear we are thinking, only some bending action is there. Okay, only some movement is there on the beam cross section. So due to that bending action or pure bending action, the amount by which the layer increases or decreases its length depends upon the position of the layer NN from the neutral axis or the neutral layer. So what it is saying, when we are calculating or when I am observing what is the change or increase in the dimension of any layer below the neutral layer, that how much quantity it has increased, how much quantity it has decreased the particular quantity decrease or particular quantity increase in the length of that layer depends on its distance or its position with respect to the neutral layer. So this is our neutral layer indication. Simply a small elemental length of delta x. That segment only I am taking. When we observe this topmost element has faced very high amount of compressive stress and it has shown maximum value of change in the length. Similarly, this bottommost portion, this bottommost layer has the highest elongation. Nothing but it has shown more increase in the length. When we are going or reaching towards end, what is happening? As when I am away, more away from neutral layer, more decrease in the length observed. Similarly, when I am more away from the neutral layer, more increase in the length of the observed. So, the position, how much it is distant with respect to the neutral layer, with that position itself, the corresponding change in the dimension occurs. In a beam which is being subjected to pure bending only, the amount by which a layer increases or decreases in its length, increase or decrease in the length, that value, the relation depends upon the position of that particular layer from the neutral axis or from the neutral layer. So from the neutral layer, if it is very far, it will have maximum change in the length. Similarly, it is very far, maximum increase in the length. Maybe it is somewhat nearer. More increase may not be observed. More decrease also may not be observed. When it is very far from that neutral layer only, more changes will be observed. Now, going into the expression. Consider a beam which is being subjected to simple bending. And in that I am taking the infinitesimal length dx. Okay. So, in that dx element, as we have already started our explanation, only we given some brief explanation only. Now we are generating the proper equation, right? Okay. In that, consider two sections AB and CD which are normal to the section and which are being parallel to each other and having a distance as dx. Okay. Now this ABCD is deformed to A dash, B dash, C dash and D dash. So this is the shape. Originally a big beam was there which is being subjected to pure bending, and in that beam I am taking a very smaller element of length dx, and that dx is in between AB and CD, and due to the bending action it has taken some shape that is A dash, B dash, C dash and D dash. So this is the new shape, and here we have indicated axis of the beam, and that axis of the beam is being indicated as neutral layer, and that neutral layer has shifted to N dash, N dash. Okay, A dash, B dash, C dash, D dash, and the original NN is indicated as N dash, N dash. Okay, up to this I am explaining. Again we will go into this picture after explaining the next point. Now the lines B dash, A dash and D dash, C dash were extended to meet the point O. See here, the line BA is extended in a straight line. As we have already mentioned, these transverse sections remain plane, right? So here it is a plane. Just it has shifted like this, but still it is a plane. So when I am extending the line to meet the next line which is coming from CD, there I have got a point O. Okay. So the point O, which is center of the curvature for the circular arc. Okay. So for that circular arc, where is the center means from these two lines where the meeting occurred. So extending, there I have observed a point of curvature or center of curvature. Okay. So this is my center of curvature by extending B dash, A dash and D dash, C dash. So meeting these two, we have got a point. Now let capital R be the radius of curvature of the neutral layer. Okay. So in this many number of layers were there. Topmost layer is there, bottommost layer is there. All those layer by layer were there. But in those layers, as we have already mentioned, I am having a neutral layer. Now from the center of curvature to this neutral layer, when we calculate the radius, that radius is indicated as radius of curvature. So, radius of curvature, capital R means it is the radius of curvature of the neutral layer. Capital R is radius of curvature of the neutral layer. Okay, this value is something, maybe some other R of A dash C dash and R of B dash D dash. Those values were different, but for the neutral layer, I am indicating R of neutral layer as radius of curvature, capital R only. Okay, capital R is radius of curvature of the neutral layer, and O is indicated as the center of curvature, and theta is the angle subtended at O, and which is in between AB and A dash B dash and C dash D dash. So angle included in between those two corners is theta, that is indicated like that, and the radius of curvature you can observe from the center of curvature to the neutral layer line. Okay, to the neutral layer line, that is the radius of curvature, and these 2 points has given the center of curvature. Okay, so when we observe the picture clearly, this generation of the picture itself very important. So I need to consider a segment, there I need to consider 2 section lines which are at a distance dx, and in this I need to indicate NL. So AB, CD and N, and then due to the application of bending we have given some new shape, and extending those 2 new lines I have got center of curvature. From the center of curvature to the neutral layer, when we calculate the radius, that is capital R, and angle included between A dash B dash and C dash D dash, that included between those 2 lines is angle of theta, and this one is for the neutral layer. Okay, so those 2 things we have explained in this step. Now I am going for the strain variation and stress variation along the depth of the beam. So from point to point along the depth, what is the strain? From point to point along the depth, what is the strain? As we have said, even though I am applying load in this condition, okay, even though we are applying the beam load in this condition, but I am observing some compressive forces, some tensile forces on the structure, right? So even though due to the application of load I am observing some compressive stresses and some tensile stresses. Okay, now this compression and tension, okay, each layer is facing some compressive stresses, some layers are facing some tensile stresses. Due to those compression and tension, I can say in this layer some strain is there. Strain means change in the length by original length of that layer. Okay, so change in the length of the layer by original length. Similarly for tensile, increase in the length of the layer by original length. In this way, strain from point to point along the depth, each layer is showing different answers that I am calculating. Now for that we are considering a layer EF which is at a distance y from the neutral layer. After bending, this layer has shifted to E dash F dash. So initially I am taking a layer of EF which is at a distance y from the neutral layer. After bending, in this EF shape I have observed as E dash and F dash. E dash F dash is the layer line. Now the original length of the EF is delta x only. See here, every element, every layer length is delta x. Okay, so each elemental length is this dx or delta x only. Sorry, dx we have given up. Anything, whatever you follow, that thing only you should have to continue. Initially, small elemental length I have taken. That elemental length, each layer is having the same length only. This EF is also initially having the same delta x length only. And initially or original length of the neutral layer, and N is also delta x only. Original length of AB, delta x. Original length of CD, every original length is delta x only. Now, after the bending action, the length of the neutral layer is N dash N dash. Okay. So, after the bending action also, neutral layer. What is a neutral layer meaning? Neutral layer will not have any expansions or any contractions. it will not have any compression or tensile forces or stress action in it. So that layer is only neutral layer. Now in the definition itself I am taking, so after bending action also, the length of the neutral layer N dash will be remain constant and unchanged. But what happening to this? When we see the structure, see here, this is the original NN, and after bending I have observed it as N dash. As it is being a circular condition, as we have already know, an arc with radius r and subtended angle theta. What is the length of this arc? Length of the arc I can indicate as r into theta. Here neutral layer NN is also same like, see here. So this neutral layer NN is having the radius r and included an angle theta. Due to these two answers, what is the length of this neutral layer? That is r into theta. Now En, Nn, delta x. Originally Nn is equal to N dash. Just now only we have mentioned Nn is equal to N dash. But N dash I can write as r times theta. N dash I can write as r times theta. So N dash measurement is equal to EF measurement is equal to everything is equal to delta x. Initially EF measurement, initially neutral layer, and after bending also neutral layer. All these values are equal to delta x only. But after the bending N dash I can give it another form also. After bending I can indicate Nn dash length as r into theta only. So this r theta I can use here also. Therefore EF is equal to Nn is equal to r theta, because N dash is equal to r theta from the second picture. From the first picture, that is delta x. From the second picture, that is r theta. But my motto is N dash is equal to Nn. That's why EF is also equal to r theta. Now after bending action, after bending, the EF layer has been after the bending action, the EF layer has become E dash F dash, as we have said initially. Initially, EF layer is having a length of delta x. After that, it has taken some new shape and new length, that is E dash and F dash. Initially, Nn is of length delta x. After bending, it has taken a shape of N dash. But its length is r theta. As Nn is equal to N dash, I can write delta x is equal to r theta, because Nn is equal to N dash from the neutral layer's definition. Okay, from the neutral layer definition, this statement I know, and this statement is giving delta x length, and this answer is giving delta r theta length. But this Nn length is equal to EF length also. See here, EF length is equal to Nn length. So every layer is having initial length same, but after coming here, E dash F dash is having some new length. Okay, so what is the length of EF? How could we calculate? Similarly like the r theta condition only. When we observe this EF layer, how much distant from the center of curvature? This E point is at a distance of r plus y. R plus y is the distance of the layer EF. From the center of curvature to the layer EF, I am observing r and y. So r plus y is the radius of this particular curve. So r plus y is the radius of the curve. Now I am taking this E dash F dash only, and it is having the radius as right? So we have said it is at a distance r and also below y. So that r plus y is the radius, and the included angle has not at all changed, that is theta only. So the new length of E dash F dash is equal to, after bending EF layer, has became E dash F dash, and its length is equal to r plus y times theta. So r plus y times theta. Now strain developed in the EF layer. What is the strain developed? Change or increase in the length by original length. So E dash F dash minus EF divided by EF. So final length, as it is elongated, E dash F dash minus EF. Final length minus initial length by initial length. So final minus initial by initial, I have got EF minus E dash F dash in this way as r theta plus y theta minus of initially r theta and the initial length as r theta. With the cancellations, we have got this answer as y theta by r theta, and cancelling thetas, we have got y by r. So what all these things? So this is the strain developed in the layer EF due to the bending action. So strain in any layer is equal to y by r. Here what is this y and what is this r? Y is distance of the layer from the neutral layer. Y is distance of that particular layer from the neutral layer. Distance of the layer from the neutral layer. You can observe here also. Distance of this particular layer from the neutral layer. And capital R is radius of curvature of the beam. Okay. And capital R, the radius of curvature, as the R is being a constant value. So we know for this beam that R is constant because the neutral layer location is constant. So as the R is constant, hence the strain in the layer is proportional to the distance of the layer from the neutral axis or the neutral layer. So distance of the layer from the neutral layer. So strain is directly proportional. What we are saying? Strain induced in a layer. How much we have got as an answer? That is y by capital R. So what is this y and capital R? As R is being constant, only y left. So strain is directly proportional to y. So what is this y? Strain in any layer is directly proportional to distance of that layer from the neutral layer. So in this condition, I have got neutral layer like this, and for the observation, I have taken another layer like this. In between these two layers, I have observed a distance of y. So strain in this layer, the quantity of strain in this layer is directly proportional to how much it is distant from the neutral layer. How much it is distant from the neutral layer. So this is the condition we have given finally. So finally, for this observation, when we represent in a picture strain in any layer is equal to y by r, it is indicating the above equation. What is saying? The variation of strain along the depth of the beam is the variation of this. The variation is like a linear condition. Simply, strain is related in single degree of y. Strain is related in a single degree y. So single power means linear or the straight line equation it will give. From the top, as we have observed, change in the length more. So more change in the length. It is high, and when it is coming near to the neutral axis, it is reducing. Again, at the neutral axis, there is no change in the length. When I am going away from the neutral axis, I am observing more change in the length. So this is the strain diagram along the depth of the beam. So with respect to depth, how the strain is changing in the form of this linear action. Why this is happening? Because any layer is very far from y, so very far from the neutral layer, it will have the maximum change in the dimension. maximum change in the dimension causes maximum strain. Okay, in this way I am generating the strain variation along the depth. In the next class we will generate stress variation along the depth. Thank you.